Look up on a clear night and pick any star. Now ask the question every human being has asked since we could ask anything. Does that star have worlds of its own? For over 2,000 years, that question had no answer. None. Because no one could possibly check. And when the answer finally came in 1995, it came from a graduate student who was convinced he had broken his instrument, and it was so strange that astronomers almost refused to believe it. The question is genuinely ancient. 23 centuries ago, the Greek philosopher Epicurus wrote it down as a certainty. There are infinite worlds, both like and unlike this world of ours. Other suns, other earths, maybe other beings. To Epicurus, an infinite universe simply had to be full of them. But Epicurus lost the argument to Aristotle. Aristotle reasoned that there could be exactly one world, ours, with everything in the cosmos arranged around it. And because Aristotle became the authority for 2,000 years, his single lonely world became official reality. Other worlds weren't just unproven, they were forbidden. Question it too loudly and it could cost you everything. In the 5080s, an Italian friar named Giordano Bruno insisted the stars were other suns, ringed by other planets, perhaps even inhabited. In 1600, the Inquisition burned him at the stake in Rome. Historians note his condemnation was mostly for theological heresies, but his infinity of inhabited worlds was right there among the accusations. Today, a brooding statue of Bruno stands on the very square where the fire burned, the Campo dei Fiori in Rome, and for 3 centuries after his death, the question of other worlds simply froze. Not because anyone answered it, because no one could. There was no conceivable way to check. The suspicion kept growing anyway. Copernicus moved the Earth from the center. Newton wrote that the stars were probably suns like ours. By the 20th century, most astronomers privately assumed other planets were out there. But assuming is not knowing. Science doesn't run on. Probably. Someone had to actually find one. And here's why finding one is so absurdly hard. Planets don't shine. They only reflect a whisper of their star's light. And the star outshines that whisper roughly 1 billion times over. Spotting a planet next to its star is like spotting a firefly hovering beside a lighthouse. Not from across the harbor, from across an ocean. Because the distances are obscene. The star this story hinges on, 51 Pegasi, sits 50 light-years away, hundreds of trillions of kilometers. Across that gulf, star and planet blur into a single point of light. No telescope of the 20th century could ever pry that firefly out of that glare. Seeing the planet directly was hopeless. So astronomers needed a trick, one of the most elegant in all of science. If you cannot see the planet, stop looking for the planet. Look at the star instead. Because a planet, it turns out, cannot orbit a star without leaving fingerprints all over it. Gravity is mutual. As a star pulls its planet around, the planet pulls back, and both of them swing around their shared balance point. The star doesn't sit still. It wobbles, tracing a tiny circle over and over, once per orbit of its unseen companion. The planet may be invisible. The wobble is not. But tiny barely covers it. Mighty Jupiter, 300 times Earth's mass, drags our sun around at about 12 meters per second. That's the top speed of an Olympic sprinter. The Earth's tug moves the sun at 9 centimeters per second, a tortoise's stroll. Now detect that stagger from 50 light-years away. There is exactly one way, and you already know it. When an ambulance rushes toward you, its siren's pitch rises. The sound waves are squashed together. As it passes and speeds away, the pitch drops. The waves stretch out. That pitch bend is the Doppler effect, and it reveals speed. Every traffic radar uses it. Light does the same thing. When a star drifts toward us, its light waves compress. The light shifts very slightly toward blue. When it drifts away, they stretch, shifting toward red. So a wobbling star breathes color blue, red, once per orbit of its hidden planet. The wobble is written in the starlight. And starlight comes with built-in measuring marks. Spread the star's light into a rainbow and it's crossed by thin dark lines, a barcode printed by the star's own atoms at exact known colors. As the star wobbles, the entire barcode slides, a hair toward blue, a hair toward red, back and forth. Measure the slide, and you've clocked the star's speed. Now for the brutal part, the precision required. To catch a Jupiter-sized wobble, you must measure that barcode shift to about 1 part in 25 million. That is like measuring a ruler a full kilometer long, and noticing it grew by half the width of a human hair. In the 20th century, that sounded like science fiction. For decades, the best spectrographs on Earth measured stellar speeds to about 1 kilometer per second, 100 times too crude. Anyone who claimed to see a planet's wobble was almost certainly measuring the shivers of their own instrument, flexing metal, drifting temperature, settling lenses. And that is exactly, tragically, what kept happening. Planet hunting became astronomy's haunted house. In the 1800s, astronomers discovered planets around the double star 70 Ophiuchi twice, and both claims dissolved under scrutiny. Again and again, wobbles were announced, celebrated, and then traced back to the telescope instead of the sky. The pattern repeated so many times that the whole subject acquired a curse. By the mid-20th century, hunting for planets around other stars was considered career poison, a swamp where careful scientists sank. Respectable astronomers kept their distance. The oldest question in astronomy had become the one nobody dared touch. But the question would not die, because it's not really an astronomy question, it's the question, are we alone? To understand why 1995 stunned everyone, you first have to feel the weight of the failures before it. And that means the most heartbreaking false alarm in the history of the search, Barnard's star. Peter van de Kamp was a respected Dutch-American astronomer at Swarthmore College, and he devoted his entire life to one star, Barnard's star, a dim red dwarf 6 light-years away, the second closest star system to the Sun. Across 4 decades, he and his students exposed more than 2,000 photographic plates of it, night after night after night. His method wasn't Doppler, it was position. If a planet swings its star in a circle, the star's location on the sky should trace a tiny corkscrew as it drifts along. So Van de Kamp measured the position of one dot of light, on plate after plate, year after year, hunting for a wiggle smaller than any ever measured. And in 1963 he announced it. Barnard's star had a planet bigger than Jupiter. The news went around the world. It entered the textbooks. Science fiction embraced it. An entire generation grew up knowing the nearest planetary system to Earth. It was one of the most famous results in astronomy. There was just one problem. Nobody else could see it. Other observatories measured Barnard's star and found no wobble at all. In 1973, 2 astronomers, Gatewood and Eichhorn, using different telescopes and independent methods, came up empty. That same year, a colleague at Van de Kamp's own observatory found the devastating explanation. John Hershey checked other stars on the same Sproul observatory plates, and every one of them wobbled in exactly the same way, in perfect sync. Real planets can't do that. The jumps even lined up with dates when the telescope's great lens had been cleaned and adjusted, 1949, 1957. The planet wasn't orbiting Barnard's star. It was living inside the telescope. Van de Kamp never accepted it. He kept publishing refinements of his phantom planets into the 1980s, and he went to his grave still believing. It's a tragedy worth sitting with, decades of meticulous, honest work, undone by a systematic error he could not see. His story hung over the whole field like a warning. This is what happens to planet hunters. The fear ran so deep that it smothered a real discovery. In 1988, a Canadian team, Campbell, Walker, and Yang, detected a wobble hinting at a planet around the star Gamma Cephei. They announced it hesitantly, then walked it back. 15 years later, better data proved the planet was real. They'd had it. The ghosts of past failures talked them out of it. Then came the strangest week in the field's history. In 1991, British astronomer Andrew Lyne announced a planet orbiting a pulsar, a dead, collapsed star. Months later, preparing to talk, he found his own error. He hadn't fully corrected for the Earth's motion around the Sun. The planet was our own orbit, reflected back at him. In January 1992, Lyne stood up in front of the American Astronomical Society, the biggest stage in the field, and retracted his own famous discovery, plainly and completely. And the room rose and gave him a standing ovation. Not for being right, for being honest. It remains one of the most moving moments in modern science. And then, in a twist almost too perfect to believe, the very next speaker walked to the same podium. Alexander Wolszczan, with radio data he and Dale Frail had gathered, announced 2 planets orbiting the pulsar PSR B157+12. Same claim, same stage, minutes later. Except these planets were real, and they are still real today. A pulsar is a spinning stellar corpse that sweeps a radio beam past Earth like a lighthouse, with timing so regular it rivals atomic clocks. Wolszczan's pulses were arriving ever so slightly early, then late, in repeating patterns the pulsar was wobbling. Planets, worlds smaller than Earth, were tugging on a dead star, and the clock gave them away. So the first confirmed planets beyond our solar system were found orbiting a corpse. Blasted, radiation-soaked worlds circling the remnant of a supernova, probably born from the wreckage of the explosion itself. It was a genuine landmark. But be honest, it wasn't the dream. Nobody gazes at the night sky and wonders about real estate around dead stars. The dream, the ancient question, was about other suns. A planet circling an ordinary, warm, sun-like star. The kind of star that could light a sky, warm an ocean, maybe cradle a world like ours. As 1995 opened, after 24 centuries of wondering, that prize remained exactly where it had always been. Unclaimed. Here's the delicious irony. The best-equipped hunters, including Jeff Marcy and Paul Butler in California, who had spent nearly a decade perfecting their technique, were braced for a marathon. Everyone knew giant planets took ages to orbit. Jupiter needs 12 years. To see one full wobble cycle, you'd wait a decade. So they collected data patiently and let it pile up unanalyzed. No rush. Because nobody imagined that a giant planet could whip around its star in 4 days. Which is why the answer to the oldest question in astronomy did not come from the biggest telescope or the richest program. It came from a modest dome in the south of France, and a 28-year-old student who thought he had broken the instrument. Michel was a Swiss astronomer at the University of Geneva, not a planet-hunting celebrity, but a quiet master of one craft, measuring the speeds of stars. He had spent 20 years building ever-finer instruments to read the Doppler slide of stellar barcodes. If anyone was going to catch a star mid-wobble, it was going to be his machines. In 1993, Mayer and his collaborators installed their masterpiece at the Haute-Provence Observatory in France, a spectrograph called LED. Fed by optical fiber, calibrated continuously against a reference lamp, cross-matching thousands of barcode lines at once, it could clock a star's speed to about 13 meters per second, bicycle sprint speed, read from trillions of kilometers away. For the first time, a Jupiter's tug was comfortably within reach. Mayer drew up a survey of 102 quiet, sun-like stars and handed the day-to-day work to his doctoral student, Didier Queloz, 28 years old, tasked with the software, the observing runs, the grind. Then Mayer left for a sabbatical in Hawaii, and while he was away, one star on the list began misbehaving, number 51 in the constellation Pegasus. 51 Pegasi. Its speed was swinging toward Earth, away from Earth, toward, away. Queloz's first thought was not planet. His first thought was, I've broken it. He was a student, alone, with a brand new instrument, watching it produce the most notorious kind of signal in astronomy, the kind that had ruined careers. He later described sweating through it, checking everything, telling almost no one. But the swing would not go away, and it repeated perfectly. Every 4 days, 5.5 hours, a full cycle, steady as a metronome. He tested the instrument fine. He checked whether the star itself was pulsing in and out. Its brightness never flickered, its barcode lines kept their shape. Night after night, the pattern only sharpened. Fold every measurement onto that 423-day rhythm, and this is what emerges. One clean, unmistakable wave. The star rushes toward us at 56 meters per second, the speed of an express train, then away just as fast, over and over, like clockwork. There is only one thing in physics that does this to a star, the gravitational grip of an unseen companion swinging it in circles. Now do the arithmetic, and try to keep a straight face. To swing a sun-like star that hard, that fast, the companion must weigh at least half of Jupiter. And a 4-day orbit puts it absurdly close in, about a 20th of the Earth's sun distance, 7 times closer to its star than Mercury is to ours. A giant planet, skimming its sun, roasting at around 1,000 degrees. Its entire year lasts 4 days. Understand, this wasn't just surprising, it was heresy. The theory of planet formation said gas giants can only be built far from their star, out beyond the snow line, where it's cold enough for ice to survive. That's where there's enough solid material to assemble a monster like Jupiter at 5 times the Earth. Sun distance? Over millions of years. In close, by the star's fire, a giant simply cannot form. Nothing that size should exist where 51 Peg's companion was sitting. Queloz finally sent word to Mayer in Hawaii, by fax, as one did in 1994, laying out the impossible, I think I found a planet. Mayer came home intrigued and skeptical in equal measure, and then nature imposed the cruelest test of all. 51 Pegasi drifted behind the sun's glare for months. All they could do was compute exactly where the wobble should be when the star returned, and wait. July 1995. 51 Pegasi climbs back into the night sky over Provence. Mayer and Queloz point the telescope, take the first new measurements, and lay them over their prediction. The points land on the curve. Right phase, right speed, as if the wave had never stopped, because it hadn't. Somewhere in that moment, dread turned into certainty. The wobble belonged to the sky, not the machine. They spent the following months trying to kill their own discovery, because that's the job. Could the star be pulsing? No. Pulsing stars change brightness, and 51 Pegs held steady. Could churning star spots fake the signal? No. Spots distort the shape of the barcode lines, and the lines were pristine. One by one, every alternative died. What survived was a planet. October 6, 1995. A scientific conference in Florence, Italy. Fitting company, Galileo City. Michael Mayer rises before a room of the world's stellar astronomers and shows the wave. 51 Pegasi, an ordinary sun-like star, has a Jupiter mass companion in a 4.2-day orbit. The first planet ever found circling another sun. The room understands instantly that, if true, everything changes. If true. Remember what this field had lived through. Van de Kamp's phantoms, retraction after retraction. Every veteran in that room had watched planets evaporate for a century. And this claim was stranger than any of the false ones. A giant planet in a 4-day orbit, a place where theory said giants couldn't exist. Extraordinary claims demand extraordinary evidence, and one team's word wasn't enough. Enter the prefix skeptics, Jeff Marcy and Paul Butler in California. The rival team with nearly a decade invested in their own precision technique and every professional incentive to catch the Swiss in an error. If 51 Peg B was an instrumental ghost, these two were the best equipped people on Earth to expose it. They booked the Lick Observatory's 3-meter telescope immediately. 4 nights, October 11th to the 15th, one full cycle of the supposed planet. Night 1, Night 2, Night 3, the star's speed climbed and fell exactly as Geneva predicted. When the final night's data came through, the curve closed on itself. Perfect. Within about a week of the announcement, the fiercest potential critics had confirmed it. The wobble was real. The planet was real. Marcy went from would-be debunker to the discovery's loudest champion almost overnight, and his team's confirmation flipped the whole field in a way no lone claim ever could. This is science working exactly as designed. Not trust, but verification. A century of false planets had made astronomers merciless. 51 Peg B walked through the fire and came out solid. The news detonated worldwide, a planet orbiting another sun. After 24 centuries, Epicurus' guess had its first data point. The planet came to be called 51 Pegasi b, informally nicknamed Bellerophon, after the hero who tamed the winged horse Pegasus, and later officially named Dimidium. 50 light-years away, the ancient question had finally cracked open. But inside the triumph sat a scandal. The planet worked, the data were bulletproof, yet by every theory of how planets form, it could not exist. A gas giant closer to its star than Mercury, its cloud tops glowing at 1,000 degrees, racing through a 4-day year. Astronomers had found their first planet around another sun, and it broke the rules of planet making on day 1. There was space to fork. Either the observation was wrong, or the theory was incomplete. The observation kept checking out, so the theory had to move. And the fix, the realization that would rescue the physics, turns out to be one of the most consequential ideas in modern astronomy. Planets do not stay where they are born. Quick recap of the rulebook it broke. Planets condense from the disk of gas and dust swirling around a newborn star. Close in, the star's heat allows only rock to survive, so you get small rocky worlds. Far out, past the snow line, ices survive, cores grow fat, and they grab gas by the ton, so you get giants. Our solar system matches perfectly, rocky worlds close, giants far. We assumed it was the template. Within months of the discovery, 3 theorists, Lynn, Bodenheimer, and Richardson, published the rescue. 51 Peg B probably did form out in the cold, 5 times the Earth, sun distance like a proper Jupiter. But then it spiraled inward, dragged by friction with the very disk of gas that built it, migrating for millions of years until it parked, scorched, in that 4-day orbit. Planets move. Migration changed how we see every planetary system, including ours. Solar systems are not built where you find them, they are shuffled, scattered, rearranged. Later work suggests even Jupiter and Saturn wandered early on before settling down. The tidy clockwork we grew up with is really the aftermath of an ancient game of gravitational billiards. Here's an honest footnote. The headline skipped. Hot Jupiters like 51 Peg B are the easiest planets to find, not the most common. A heavy planet, close in, whipping around fast, makes the biggest wobble in the shortest time, so of course we found those first. We were looking under the lamppost. In truth, hot Jupiters orbit only about 1 star in 100. They're rare. They were just loud. Then the floodgates opened. Marcy and Butler raced back through their years of stockpiled, unanalyzed data. Remember, they'd been pacing themselves for a decade-long marathon and found planets already sitting in it, 70 Virginis B, 47 Ursae Majoris B, within months. By 2000, dozens of worlds were known. Every single one a place that hadn't existed, for us, the year before. And a second trick during the hunt. If a planet's orbit happens to be edge-on as seen from Earth, then once per orbit the planet crosses the face of its star, and the star dims. Barely. A fraction of a percent. But it dims on schedule, every orbit. A tiny, punctual eclipse. Astronomers call it a transit. You're watching a planet's shadow. In 1999, it worked for the first time. The star HD 29458, already suspected from its wobble of holding a hot Jupiter, dimmed by 1.5%, exactly when the wobble said the planet should cross. 2 utterly independent methods, 1 planet. Any lingering doubt about exoplanets died that night. And the depth of the dip handed us something new, the planet's actual size. Transits scale magnificently. A wobble must be measured star by patient star, but a camera can watch 100,000 stars at once, waiting for any of them to wink. That was the whole idea behind a space telescope named for the man who first wrote the laws of orbits, Kepler. It launched in March 2009 with one job: stare and count the winks. Kepler stared at one patch of sky near the constellation Cygnus for 4 years, monitoring about 150,000 stars simultaneously, measuring their brightness to parts per million. It found planet after planet after planet, over 2,600 confirmed worlds from that single stare, with thousands more candidates. Planets, it turned out, weren't rare at all. They were everywhere we looked. And Kepler found kinds of worlds we don't even have. Between the size of Earth and the size of Neptune lies a whole zoo, super-Earths and mini-Neptunes, and they turn out to be among the most common planets in the galaxy. Our solar system contains exactly none. Read that again. The most ordinary type of planet in the Milky Way is one our system skipped. We're the odd ones. Watch the numbers tell the story. 1 planet around a sun-like star in 1995, about 50 by the year 2000, 1,000 by 2013. Then the Kepler avalanche, 5,000 by 2022. Past 5,500, past 6,000, and still climbing every single week. In one human generation, do other worlds exist? Became, we can barely keep count. Now plot every known world at once. Each planet by its mass and its distance from its star, and you can see 1995 still echoing. There's the crowd of hot Jupiters, huge worlds huddled scandalously close to their stars, exactly where the old theory drew a blank. There's the vast swarm of smaller worlds. And there are our own 8, looking positively lonely on the map they used to define. Then came the statistic that settles the ancient argument outright. In 2012, an international team used a technique called microlensing, planets revealing themselves by subtly bending starlight, to run a galactic census. The result, on average, every star in the Milky Way has at least one planet. Planets don't just exist. Planets outnumber stars. Hundreds of billions of worlds in our galaxy alone. Stop and feel what that does to the night sky. Every star you can see tonight, every single one, almost certainly has planets. That red one. That blue one. The dim one you can barely make out. For all of human history, the sky was a field of lights. It is actually a field of places. And what places? We found worlds where the day side runs hot enough to vaporize iron, and the iron may fall as rain on the night side. Worlds orbiting 2 suns at once, with double sunsets straight out of fiction. Worlds fluffier than cork, worlds denser than lead, lava worlds, ocean world candidates, planets older than our galaxy's spiral arms. The universe's imagination beats ours. It isn't close. But the worlds we ache for are quieter ones. Around every star there's a band, not too close, not too far, where a rocky planet could keep liquid water on its surface. The habitable zone. The Goldilocks band. Kepler's census produced its most breathtaking number here. Small planets in that band appear to be common. Potential Earths are not miracles, they're inventory. In 2016, the search came home. Around Proxima Centauri, the nearest star to the Sun, our next-door neighbor, 4¼ light-years away, astronomers found a planet at least as massive as Earth, orbiting in the star's habitable zone. The closest star in the entire universe to us has its own world. The frontier, it turns out, starts at the property line. The next year, TRAPPIST-1, 7 Earth-sized planets around one small red star 40 light-years away, several in or near the habitable zone, a whole miniature solar system, packed so tight that from one planet's surface, its neighbors would hang in the sky like moons. 7 worlds, 1 star. Planetary systems aren't just common, they're generous. And now, we've begun reading their air. When a planet transits, a sliver of starlight filters through its atmosphere on the way to us, and the gases stamp their barcode into that light. The James Webb Space Telescope is doing this today. Water vapor, carbon dioxide, methane, sulfur chemistry, detected in the skies of planets we will never visit, printed in starlight we caught in a mirror. You can see where this is pointed. Somewhere out there may be an atmosphere whose chemistry doesn't add up. Oxygen and methane together, gases that only keep company when something is alive and breathing. No one has found that yet. But for the first time in the whole history of our species, is anyone out there? Is not a meditation. It is a measurement. Scheduled, funded, and underway. And every bit of it, the transits, the space telescopes, the atmospheres, all 6,000 and counting worlds, traces back through one doorway, a wobble of 56 meters per second, found by a student who thought he'd broken the machine, checked and rechecked until doubt ran out. 51 Pegasi b didn't just add a planet to the catalog. It created the catalog. Which is why, on the morning of October 8, 2019, in Geneva and in Cambridge, 2 telephones rang with a call from Stockholm. The 2019 Nobel Prize in Physics. One half went to James Peebles for the theory of the universe's evolution. The other half went jointly to Michel and Didier Queloz, in the committee's words, for the discovery of an exoplanet orbiting a solar-type star. One planet, one wobble. The prize committee understood exactly what that wave had been worth. 24 years after that afternoon in Florence. Didier Queloz, the doctoral student who spent months terrified that his signal was a bug, who sweated over calibration checks alone in Provence, stood in Stockholm as a Nobel laureate. The anomaly he was tempted to explain away had become one of the most important measurements of the century. It's worth pausing on how this discovery actually happened. Not with the biggest telescope on Earth, a modest 1.93-meter instrument, not with the biggest budget, a cleverer spectrograph, and not by the team with the most data, but by the one that looked hardest at the point that made no sense. Queloz's first instinct, "I've broken it," wasn't weakness, it was the discovery working. Distrusting your own thrilling result is the discipline that separates science from wishful thinking. It's what Van de Kamp, tragically, could not do. Queloz doubted, tested, doubted again, and only when doubt ran out of places to hide did he believe. The dread was the method. There's a deeper lesson in what they found. If the universe only built solar systems like ours, the first exoplanet would have taken another decade of patient watching. Remember, everyone was braced for 12-year orbits. Instead, the universe turned out stranger and more inventive than our theories, and its rule-breaking planet is precisely what handed us the early answer. Nature rewarded the search by refusing to match the textbook. Go stand in the Campo de Fiori in Rome some evening, where they burned Giordano Bruno for, among his heresies, an infinity of inhabited worlds. His statue faces down the square, hooded and unbowed. More than 4 centuries after the fire, robotic telescopes on 2 continents and in space log new planets around other suns every week. History has rendered its verdict on that particular argument. Epicurus versus Aristotle is settled too, after 23 centuries, and the old Greek optimist one going away. Worlds are not the exception, worlds are the rule. Wherever a star ignites, planets seem to follow as naturally as sparks follow a fire. A universe that makes stars, it turns out, cannot seem to stop itself from making places. And our own solar system got reframed in the process. We are not the template. We are one arrangement among hundreds of billions, and in some ways an unusual one, no super-Earth, no hot Jupiter, our giants parked politely far out, our small blue world left undisturbed for 4 billion quiet years. Whether that quiet is common or precious, that's one of the great open questions our grandchildren get to answer. Because the ancient question has a successor now. Not, are there other worlds? That one is done, answered carved in stone. The new question is there another Earth, and is anything looking back? And unlike Epicurus, unlike Bruno, unlike every generation of wanderers before us, we are the first who get to attack that question with instruments instead of arguments. The instruments are coming. Space telescopes are reading exoplanet atmospheres now. New observatories are being designed with one explicit goal, to take an actual photograph of an Earth-like world around a sun-like star, to finally, literally, see the firefly beside the lighthouse. The technology that was hopeless in 1995 is on the drawing boards for the 2030s and 40s. Imagine that photograph. A single pale blue pixel sitting beside a smeared-out star on a poster in every classroom on Earth. One pixel that means oceans maybe, weather maybe, company maybe. The picture of another Earth is now an engineering project, with a budget line and a launch decade, rather than a dream. Read that sentence to your grandparents and watch their faces. Measure the speed of all this. A person born in 1995, the year of 51 Peg B, turned 30 as the count passed 6,000 worlds. One human childhood ago, the number of known planets around sun-like stars was 0. 0 for 200,000 years of human beings looking up. Then 1. Then 6,000. That is not gradual progress. And notice what actually broke it. Not one genius, but a chain of temperaments, Van de Kamp's cautionary error. Line's heroic retraction. The Canadian team's too careful caution. Queloz's honest dread. Marcy's ruthless verification. The field crawled out of its haunted century not by dreaming harder but by doubting better, sharper instruments, and the discipline to attack your own results before the universe does. Be kind to the failures in this story. The field's success is built from them. Van de Kamp was wrong but not foolish. His error taught precision. Line's public retraction earned a standing ovation and set a gold standard for scientific honesty. Campbell and Walker were right and too scarred to insist. Every stumble calibrated the instrument that finally got it right. Meanwhile, 50 light-years away, 51 Pegasi is still doing it. Tonight? Right now. That star is swinging through its little circle at express train speed, 4 days, 5.5 hours per lap, exactly as it has for billions of years, whether or not anyone measures it. Any good spectrograph on Earth can still hear that heartbeat. It is the first page of the catalog, and it will never stop being written. So here is what you now know when you look up. More planets than stars. Hundreds of billions of worlds in this one galaxy. Every constellation you can name is crowded with invisible geography. Deserts no one has crossed, ice fields no one has mapped, storms bigger than Earth that no eye has ever watched. The night sky is not a ceiling. It is a continent line on the map of an unexplored ocean. Think of the sunsets happening right now. Double sunsets over desert worlds with 2 suns, iron-gray sunsets on planets where the clouds are metal, slow crimson sunsets under old red stars that will outlive every star like ours. Uncountable, unwitnessed, going on at this moment. That is what 1995 actually bought us, the license to say those sentences as fact, not fantasy. We began with a child under the night sky, asking whether the stars have worlds. Every generation of our species asked it. Every generation got silence. Ours is the first. The first. That gets to answer, yes. Thousands found, billions implied, everywhere we look. If you ever want to feel the privilege of being alive right now, that's it. We are the ones who found out. And the answer was earned, by centuries of stubborn wondering, by a haunted century of failure, and finally by 2 people in Provence who took an impossible wobble seriously enough to test it to death before daring to believe it. Mayer and Queloz's planet did more than exist. It flung open a door that will never close again. Stay curious about anomalies, about the data point that can't be right. 51 Pegasi. B spent its first weeks as a suspected instrument error. It ended as a Nobel Prize and the founding stone of a new science. The universe's best secrets seem to arrive dressed as mistakes, and they wait, patiently, for the one person who checks instead of shrugs. And stay curious about the sky itself. It is so much deeper than it looks. Every point of light up there is a sun. Nearly every sun carries worlds, and on some of those worlds perhaps something is standing under a strange sky tonight, looking at a dim yellow star and its constellation, wondering the same ancient thing about us. If this story stuck with you, do 2 quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments, which part of this surprised you the most? I read every single one. So keep exploring. Your next story is just 1 click away. I'll see you there.